Right now, our entire galaxy is falling at 600 kilometers per second toward a region of the sky we cannot directly see. We have measured the motion for 40 years. We still do not know exactly what is pulling us. The direction has been mapped. The source is partially hidden behind the disk of our own galaxy, and it is much larger than anything we expected to find in our cosmic neighborhood. The discovery started with the cosmic microwave background. The CMB is the radiation left over from the Big Bang, filling all of space, almost uniform in temperature in every direction. Almost. In the 1970s, more precise measurements revealed a small but unambiguous asymmetry. The CMB looked slightly warmer in one direction and slightly cooler in the opposite. This is called the CMB dipole. The interpretation is straightforward. The asymmetry is a Doppler effect. Our motion relative to the CMB warms it ahead of us and cools it behind. From the size of the asymmetry, you can extract our speed.
The signal itself is small. The temperature difference between the warmest and coldest points of the dipole pattern is only about 0.003 of 1%. But the precision of the instruments, first the COBE satellite in the early 1990s, then the WMAP mission, and finally Planck, made it one of the cleanest results in modern cosmology. That speed turned out to be roughly 627 kilometers per second relative to the CMB rest frame. This was strange. The expansion of the universe was supposed to drag galaxies apart at predictable rates. Any motion on top of that expansion, what cosmologists call peculiar velocity, was expected to be small. A galaxy might wander 100 kilometers per second relative to its neighbors. 600 kilometers per second was enormous. Something was pulling on the entire local group of galaxies, and that something had to be massive enough to overcome the homogeneous expansion of the universe on tens of millions of light-years of scale.
In 1987, a team of 7 astronomers, Alan Dressler and collaborators, who came to be called the 7 Samurai, published the paper that mapped this flow. They used what was then a new method, measuring the redshifts and distances of thousands of galaxies in our local volume to infer the gravitational potential pulling them. What they found was a coherent flow of galaxies, including ours, toward a region of the sky in the constellation Centaurus. At first, the result looked wrong. A peculiar velocity of 600 kilometers per second was several times larger than any standard cosmological model predicted for a galaxy our size. Within months of the announcement, the team faced detailed criticism. Other groups reanalyzed the redshifts, checked the distance estimators, and looked for hidden systematic errors in the photometry. The signal survived every test. The flow was real, and the implication was hard to escape. There was a large concentration of mass, somewhere in that line of sight, exerting gravitational influence on a scale we had not anticipated.
They named what they were finding the Great Attractor. They estimated its location at roughly 220 million light-years from Earth. They could not see it directly. The line of sight passed straight through the dense, dusty disk of our own galaxy, a region astronomers had long called the zone of avoidance because optical surveys could not penetrate it. The Great Attractor was inferring its existence by its gravitational effect on galaxies we could see, distributed on either side of the obscuration. It was a gravitational fingerprint with no visible source.
The zone of avoidance is real. Our galaxy is a disk seen edge-on from inside. Stars, gas, and dust block visible light from anything behind it. Roughly 20% of the sky is effectively opaque to optical telescopes. Entire galaxies fall inside this blind region. Mafe 1 and Mafe 2, two large galaxies less than 10 million light-years from us, were missed by every optical survey before their discovery in 1968. They sit almost directly behind the galactic plane. Behind them, further out, the situation only gets harder. Until the late 20th century, vast volumes of the local universe were essentially uncharted, not because they were too distant, but because we were looking through our own galaxy at them. For decades, the Great Attractor sat in the middle of that opaque region. Two technologies broke the impasse. First, infrared and radio observations. Both wavelengths penetrate galactic dust much better than visible light. Surveys at these wavelengths started filling in the map behind the zone of avoidance in the late 1990s and 2000s. They revealed galaxy clusters and superclusters that had been invisible to optical instruments.
Second, X-ray astronomy. Massive galaxy clusters glow in X-rays because their intra-cluster gas is heated to tens of millions of degrees. An all-sky X-ray mission known as ROSAT, launched in the 1990s, and later XMM Newton and Chandra observations, mapped X-ray bright clusters across the entire sky, including the obscured region. The picture that emerged was clearer, but more complicated. The Great Attractor was not a single object. It was a region containing a concentration of clusters, including the Norma cluster, Abell 3627, sitting close to the geometric center of the predicted gravitational pull. But the Norma cluster, while massive, was not big enough to account for the full peculiar velocity. The math required more mass than the visible local concentration could provide. So they looked further, and about 3 times further out, at roughly 650 million light-years, they found it, the Shapley Supercluster.
Shapley is one of the most massive concentrations of galaxies in the observable universe. It contains an estimated mass of 100 quadrillion solar masses, that is 10 to the 17th power, distributed across multiple major clusters. By the late 2000s, careful analysis of cosmic flows showed that Shapley accounts for the majority of the peculiar velocity attributed to the Great Attractor. The Great Attractor is real. It is a local overdensity, but it is partly a foreground feature in a larger gravitational landscape dominated by Shapley. In other words, the Milky Way is not just falling toward the Centaurus region. It is falling towards something much larger, 500 million light-years away, that the Centaurus region partly hides from view. In 2014, a team led by Brent Tully at the University of Hawaii published a paper that did for our cosmic neighborhood what plate tectonics did for geography. Instead of relying on visible galaxy distributions, they mapped the velocity field, the actual motion vectors of thousands of galaxies in our local volume, and identified the gravitational watershed we belong to. The result was a structure they named Laniakea. The word is Hawaiian for immeasurable heaven. Laniakea is a supercluster containing approximately 100,000 galaxies, spanning about 520 million light-years. The Milky Way sits near its edge. The Great Attractor is at its dynamical center. Everything inside the Laniakea boundary, including us, is gravitationally drawn toward this central region. Galaxies just outside the boundary are pulled toward other superclusters, Perseus Pisces, Coma, Shapley. The Laniakea definition rests on the velocity field. A galaxy belongs to Laniakea if its peculiar velocity vector points inward toward our central attractor region. Galaxies whose vectors point outward belong to something else.
This reframes the question. The Great Attractor is not the destination of our motion.
It is the local low point in a much larger landscape that includes Shapley as the dominant mass concentration. Our galaxy, the local group, the Virgo Supercluster, and the Centaurus complex are all sliding down the same gravitational slope. The motion is real. The structure is real. The math has been refined for 50 years. What we still do not know precisely is the total mass involved, because the most massive concentrations remain partly hidden behind the zone of avoidance and partly beyond the limit of current peculiar velocity surveys. New all-sky surveys, the next-generation X-ray telescope, E-Rosita, the Vera Rubin Observatory in optical, and future radio surveys with the square-kilometer array will refine the map. Every revision so far has pushed the gravitational source further out and increased the inferred mass.
The pattern is consistent. Every time the resolution improves, more mass appears on the far side of every survey. The Great Attractor turned out to be the foreground of Shapley. Shapley itself sits in a region where even larger scale concentrations have been hinted at but not yet mapped. Early signals from peculiar velocity surveys at 600 million to 1 billion light-years suggest the gravitational landscape continues to deepen further out. The honest answer to what is pulling our galaxy is this: not a single object. A hierarchy of mass concentrations, the largest of which is Shapley, partially screened from us by our own galactic disk, and producing a coherent flow that has been carrying every star within Laniakea, including the Sun and everything it has ever orbited, in one direction for as long as cosmology has been a science. What it means in practical terms is more humbling than dramatic. Our motion through this gravitational basin does not change anything we can directly observe in a human lifetime. The Sun has already drifted hundreds of thousands of kilometers since you started watching this video, and it will not arrive anywhere recognizable for hundreds of millions of years. The expansion of the universe continues. The far reaches of Laniakea are also slowly receding from us. What the maps of cosmic flow really show is not a destination, but a current. A description of which way the substrate of the universe is sliding, all of it together, on a scale where stars are atoms and galaxies are dust grains.